Hello, good morning, dear students. I am here, Lalit Kumar P. Bhaiya, Associate Professor, Electronics and Telecommunication Engineering Department, Bharati College of Engineering and Technology, Durg. Dear students, in last video, that is in video number 49, we have seen the part 2 of the digital electronics, that is the logic gates. As far as your syllabus is concerned, you must know the basic digital electronics. We have seen the basic digital electronics in part 1. Then we have seen 2 or 3 gates in part 2. Let us review what we have seen in part 2. Logic gates. What are the logic gates? And different gates: OR gate, AND gate, NOT gate, NAND gate, NOR gate, XOR and XNOR gates. We have seen introduction, how these gates are used for the Boolean algebra. Positive and negative logic designation we have seen. We have seen the first NOT gate called as an inverter and the truth table of the inverter operation and simple numerical on the inverter, this one with the waveforms. Logic expression for the inverter, that is X is equal to A bar, where A is the input. A bar indicates the inversion. We have seen the application of the inverter also. Then we have gone through the AND gate. AND is just a logical multiplication. This is the symbol of the AND gate which we have seen. Distinctive shape and rectangular outline. And AND gate is equal to X is equal to A dot B, which we have seen, A ANDing B. And we have also seen this truth table. Whenever both the inputs are positive, the output is positive, otherwise it is 0. That we have seen. AND gate may be 2 input, 3 input, 4 input. And for 2 input, 2 to the power 2, that is 4 combinations are there. For 3 input, 2 to the power 3, 8 combinations. For 4 input, 2 to the power 4, that is 16 possible combinations for the ANDing operation. This is, we have seen for the 3 input AND gate. And we have this 3 input 8 possible combinations. Then operation with the waveform, this we have seen for the AND gate, and this is example for the AND gate with the waveforms, input A, input B and X is the output. This is one example we have seen. This is the another example. And logic expression for the AND, X is equal to A into B, that is A dot B. A dot B, or simply you can write A, B. This is ANDing, A ANDing B. Similarly, for 4 inputs, X is equal to A dot B dot C dot D, or A ANDing B ANDing C ANDing D. This is the examples. The AND gate as an enable or inhibit device is the application for the AND gate. Number of applications are there. You can use AND gate. This application we have seen for sending the input A and the enable of 1 second timing. Within this 1 second you will get the output. Then next gate is the OR gate. OR is called as the logical addition type. The OR gate is another of the basic gates from which all logic functions are constructed. An OR gate can have 2 or more inputs and performs what is known as logical addition. After completing the section, you should be able to identify an OR gate by its distinctive shape symbol or by its rectangular outline symbol. Describe the operation of an OR gate. Generate the truth table for an OR gate with any number of inputs. Produce a timing diagram for an OR gate with any specified input waveform, and write the logical expression for an OR gate with any number of inputs. You can discuss the number of examples of OR gate applications. An OR gate has 2 or more inputs and 1 output, as indicated by the standard logic symbol as shown in figure. You can see this figure. This A and B are the inputs. This is the shape of the OR gate. You will get X is the output. This is distinctive shape and this is a rectangular outline for the OR gate. AB greater than or equal to 1. This is X. But we are not using this one. This OR gate we use in general symbols. Where OR gate with 2 inputs are illustrated, and OR gate can have any number of inputs greater than 1. Although both distinctive shape and rectangular outline symbols are shown, the distinctive shape OR gate symbol is used in this our digital electronics books. Operation of an OR gate. An OR gate produces a high on the output when any of the inputs is high. The output is low only when all of the inputs are low. This is a one-line simple operation of the OR gate. An OR gate produces a high on the output when any of the inputs is high, and the output is low only when all of the inputs are low. That means when if 2 inputs are there, output X is high when either input A or input B is high, or when both A and B are high. X is low only when both A and B are low. You can see, if this is low, then only this is low. If any one of these high, output will be high. If any one of these high, output will be high. If both are high, the output will be high. So this is the operation of the OR gate, and you can give this operation on the truth table. This is the truth table, 2 input OR gate truth table. 2 input means 4 combination, 2 to the power 4. A and B are the input and X is the output. So if both the inputs are low, output is low, and any one of the input is high, output will be high. This is called as OR gate. That means in rough language you can say 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus is 1. Carry 1. So this type of truth table of OR gate and operation you can remember for using the OR gate with the supply. And this is the operation with the waveform inputs. You can see this is A input and this is B input. Output is only low when both A and B are low. In this case, you can see this is low output here, low input A, and this is low input B. So here only you will get the low output. Otherwise, you will get high output everywhere. Only when both the inputs are low, you will get the low. Otherwise, here high, here high. So in terms of waveform, you can explain the operation of the OR gate, right? So this is about the OR gate. This is another example of the OR gate application type example. If the two input waveforms A and B in figure are applied to the OR gate, what is the resulting output waveform? Again, you can have the simple. When both the inputs A and B are low, you will you can see at this particular state, this is low and this is low, so you will get the low. And again you can see this is low and this is low, you will get the low. Here it is low, B is also low, you will get the low. And anywhere output will be high. So you can draw the waveforms also very simply for the OR gate. Logic expression for an OR gate. The example of the logic OR gate is example expression of the logic OR gate. X is the output. X is equal to A ORing with B. This plus sign indicates the ORing in digital arithmetic. That is A plus B. A plus B means A ORing with B. And this is the operation. 0 plus 0 is equal to 0. That is low plus low is equal to low. Low plus 1 is equal to 1. 1 plus 0 is 1. 1 plus 1 is 1. I am saying here plus, but it is actually the ORing. Boolean addition. This is called as Boolean addition, digital addition. So 0 OR with 0, that means 0. 0 OR with 1 is 1. 1 is OR with 0 is 1. 1 is ORing with 1 is 1. So this is the operation of the OR gate, and you can say this is also the truth table. This is the truth table of the OR gate shown here. A and B are the inputs, and this is A or B. A ORing with B is equal to X is the output. So what is the operation? When both the inputs are low, output is low, otherwise it is high. So this is the truth table of the OR gate. You can remember this truth table, a very simple truth table. An application. In application, this is shown here. 3 input OR gate is there. This is a simplified intrusion detection system using an OR gate. Is an application. Here open door or windows sensors. These are, and this is the OR gate. So what is the output of the OR gate? When all the inputs are low, that is door closed, then output is 0. Output is low. When one of the door is open, here that means high, the output will be high. So here you can, and when the output is high, the alarm will be detected. Alarm is connected to the output of the OR gate. So this alarm will be on when output of the OR gate is high. And output of the OR gate is high only when one of the input is high. That means any one of the door is open from these 3 windows. The signal will be high from one of the window, output will be high, and that will alarm the signal. If all the doors are closed, that means 0 position, output will be low, no alarm will be there. So this is a very good example of the OR gate you can show here. Then NAND gate. The NAND gate is popular logic element because it can be used as a universal gate. That is, NAND gates can be used in combination to perform AND, OR and inverter operations. NAND gates can be used in combination to perform AND, OR and inverter, that is NOT gates, and OR NOT gates operations. The universal property of NAND gate will be examined thoroughly in the previous chapters here. After completing this NAND gate, you should be able to identify a NAND gate by a distinctive shape symbol or by its rectangular outline symbol. Describe the operation of the NAND gate. Develop the truth table for a NAND gate with any number of inputs. Produce a timing diagram for a NAND gate with any specified input waveforms. Write the logic expressions for a NAND gate with any number of inputs. Describe NAND gate operation in terms of its negative or equivalent. And we can discuss the examples of a NAND gate. You can see this is a NAND gate shown here, the symbol of the NAND gate. This is the symbol here, bubble is shown here. So it is AND operated with inverter, that is NOT gate. A and B are the input, X is the output. This is the AND gate and this is the NOT gate. This combinedly forms the NAND gate, and followed by NOT is the NAND. And this is the rectangular outline symbol. You forget about this distinctive shape 2 input NAND gate. You have to remember this one, NAND gate. So this is the symbol of the NAND gate, and operation is very simple. For a 2 input NAND gate, output X is low only when input A and B are high. X is high when either A or B is low, or when both A and B is low. So what is the operation? You can see here. If both the inputs are high, here you can see A and B are high, output will be high. Output of the AND gate will be high, and you will get low here. If both the inputs are low, the output of the AND gate will be low, and you will get X will be high. So what is the operation? When both 2 inputs NAND gate is used, the output X is low only when input A and B are high. And X is high when either A or B are low, or when both A or B low. So only the condition of the output of the NAND gate is that when both the inputs are low, then output will be high. Otherwise, output will be low. This is the operation of the NAND gate. So you can see, if both the inputs are low, then output will be high. If here one of the input is high, output will be high. One of the input is high, output will be high. Both the inputs high, then output will be low. This is the case when both the inputs are high, output will be low. Otherwise, the output will be high. And this is the truth table of the 2 input NAND gate. So you can see in 2 input NAND gate, if both the inputs are low, if both the inputs are high, then output is low. Otherwise, output is high. If both the inputs are high, output will be low. So this is the NAND gate, and this is the symbol for the NAND gate, it is called as a universal gate. Because using this NAND gate, we can prepare any of the gates. Any of the gates we can prepare using the NAND gates. That's why we can call it as a universal gate. Right? And this is the waveform shown here for A and B. And according to the truth table, if both the inputs are high, then output will be low. So you can see here, this part of B is high, here high, you will get here low. Otherwise, everywhere the output will be high, like this. Only at the both inputs are high, output will be low. Both inputs are high, output will be low. So this input is high, this input is high, output is low. This input is high, this input is high, output will be low. This input is high, this input high, output will be low. This input is high, this input is high, output will be low. So accordingly, this you can give about the NAND gate. For a 2-input NAND gate performing a negative OR operation, output X is high when either input A or B is low, or when A or B are low. This is 2-input equivalent operation of NAND gate. This is our usual NAND gate, standard NAND gate which we are using. This can be converted with negative OR. Negative OR means these 2 inputs are inverted, not, and then given to the OR gate. So this can be converted. This is also called as a NAND gate, equivalent NAND gate in terms of OR gate. So that's why I am saying the NAND gate can be used for preparing any of the gate. That's why it is called as a universal gate. Another universal gates are there that we will see later on. And this is a logical expression for the NAND gate. What is the logical expression? X is equal to AB bar, A dot B whole bar is the expression for the NAND gate. That means when both the inputs are low, 0.000 bar is 1, output is high. You can see when both the inputs are low, output is high. One of the input is low, output is high, but both the inputs are high, then output is low. When this is 1, then 1.1 bar is equal to 1 bar, and that is equal to 0. So this is the truth table for the NAND gate. So this NAND gate you can see here. Then we will go for the NOR gate. It is a useful logic element because it can also be used as a universal gate. This NOR gate is another universal gate after NAND gate. NOR gate can be used as a combination to perform the AND, OR and NOT operations. That is inverter. The universal property of the NOR gate can be used here. So again, for the NOR gate, this is the symbol. That is OR followed by NOT. This is OR followed by NOT. It's called as a NOR gate. OR followed by NOT. AND followed by NOT is the NAND gate. Similarly, OR followed by NOT is the NOR gate. So this is the symbol for the NOR gate. Bubble is shown here. Bubble indicates for the NOT operation. So this NOR gate you can go through this, and this is the operation for the NOR gate. You can see here, this is the truth table for the NOR gate, and here for 2-input NOR gate, output X is low when either input A or input B is high, or when both A and B are high. X is high only when both A and B are low. So output will be high only A and B are low. So you can see in only this case, low, low, output will be high. Otherwise, the output will be low. So this is the operation of the NOR gate. This is the truth table for the NOR gate. And NOR gate you can write A plus B whole bar. A plus B is the operation of the R, and you can give the bar, that is the expression for the NOR gate. It is not shown here, so I will tell you here. A ORing with B whole bar is the representation of the NOR gate. X is equal to A plus B whole bar, that is NOR gate operation. This is truth table. When both the inputs are high, output will be low, and when both the inputs are low, the output will be high. Otherwise it is 0. Or simply you can say, for two input NOR gate, if both the inputs are low, then output will be high, otherwise it is low. This is the example in terms of the waveform. You can go through this example. This is also example. And this is the logical expression. X is equal to A plus B whole bar, which I have already told you. You can go through this expression and truth table. Thank you very much for today. Remaining part we will see in the next video, and other parts we also go for the next video. Thank you very much. Thanks a lot.